draw the Lewis structures for, wow, that's a lot of them. Draw Lewis for TeCl4, ICl5, PCl5, KrCl4, and XeCl2, okay, which exhibits a bond angle that's approximately 120, around 120 degrees. Which compound exhibits D2sp3? I think they wrote that wrong. They want which exhibits sp3d2 hybridization, and which, wow, this is a big question, which have a square planar, okay, and which are polar. So, wow, we're gonna be here for a little bit, but that's perfectly fine. Okay, so we're gonna start off with TeCl4. Okay, so Te is tellurium, which is all the way down here. Okay, and we have chlorine. So TeCl4. We're still gonna go over, you know, things like the electron, electron configuration and such, in regards to like how many electrons they contribute. You know what? Actually, for this question, considering that we have quite a bit of ground to cover, we're gonna skip that. We're just gonna go simply by the where it's located on the periodic table. So it's the 16th column for tellurium, so it provides 6 electrons. Chlorine's on the 17th column, so it has 7 electrons. There's 4 of chlorine, so it's going to be 7 times 4, and then plus that 6, we need to account for 34 electrons. So let's start out by drawing it. Okay, so tellurium, it's in the middle. Give yourself enough space. Okay. The chlorine is going to be on each end. And tellurium, just letting you know right now, is going to be one of those that breaks the octet rules. But first, let's fill out the chlorines at the end. It's sharing one of its 7, so 2, 3, 4, 5, 6, 7. Perfect octet filled. Same thing here. Another octet. 4, 5, 6, 7. Another octet. 2, 3, 4, 5, 6. Another octet. So now tellurium is so far only sharing 4 of its 6. So it's going to have 5, 6 right there. So tellurium actually technically has 5 things bonded to it. Okay. So that's for tellurium. We're going to stop there because we're going to actually draw everything else before we get into in terms of the electron geometry of each one. Okay. And we have, I hope I wrote this right, ICl5. Is it ICl5 or ICl3? ICl5, okay? So, that's what we have for tellurium, okay? ICl5, okay, is going to be ICl5. Chlorine still offers 7, and iodine actually offers 7, so we need to account for 35 electrons, okay? So kind of following the same for tellurium, we have iodine in the center, okay? And we're going to have each side having a bond. But there's 5 chlorines, so just as how I kind of have that other one in red for tellurium, the 5th one, because iodine also doesn't care about the octet rule, is going to be like that. Whoops, so it's not 35. Definitely did the math wrong. It's going to be 7 times 6. Did not account for, I thought we're still dealing with 4 chlorines, so it's going to be actually 42 electrons. So we're going to have quite a bit we got to count through, okay? So for tellurium, before I actually go ahead, I'm going to make sure we actually have 34. Okay, so there's 8 on each chlorine. So 8, 8, 8, 8. So that's 32. And then 2 more on that tellurium, which is 34. Perfect. So with that being said, let's fill out the octet for each chlorine, because it is sharing one of its 7. So the other 7 are going to just be filled in. Okay. All right, and then for this last chlorine we have, it's going to be a little bit of a squeeze here, like that. And then iodine is actually sharing right now 5 of its 7. So we're going to have, again, 6, 7. So with that being said, we have 8 times 5, which is going to be 40. Okay, plus 2 more, 42. Perfect. Then we have PCl5. Okay, so we have PCl5. And just to make sure that's actually what we're dealing with. Yep, perfect. So we have another one in the middle, phosphorus. Okay, and we have sharing 1 each. Maybe I should give myself more space. Actually, I'm gonna actually move this all the way to this side, because I'm gonna be writing down the shape and everything right under it. Okay, so I'll just put it like that. All right, so with that being said, we have a chlorine here, a chlorine there, chlorine here, and then they said there's a 5th one, so gonna be a little bit of squeeze, chlorine there. So the same octet rules being filled. So 1, 2, 3, 4, 5, 6 of the 7. Same here, and the same here, and then same here, and then for that extra chlorine, same thing. All right, and kind of skipped ahead. PCl5. Phosphorus can only donate 5 because it's on the 15th column. Chlorine still is 7, and there's 5 of them. So 7 times 5 is 35, plus 5, 40. So we have 40 electrons. And if we actually go around 8 times 5, because each chlorine is the octet rule, we do get 40. So this is perfect. Now for the next one, we have Krypton Cl4. Okay. So, ooh, wow, yeah. So just can't run out of steam here. Krypton Cl4. Okay, so Kr. Okay, has those bonds there. I'm just making sure. Just have to double check that we actually have the right amount. Okay, so we have now. Okay. Chlorine, okay, and then we're gonna now add the extra electrons. Let's start with krypton in the middle. It's right now sharing 4 of its 8, so 5, 6, 7, 8. Okay, so krypton is done. Krypton Cl4, it's 8 being donated because it's on the 18th column. Chlorine is still 7 times 4. So 7 times 4 plus 8. We have 36 we need to account for. Okay. So with that being said, we have each chlorine has 1 of its 7 electrons being shared. So now it's 2, 3, 4, 5, 6, 7. Same for each chlorine. Okay, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, so with that being said, 8 times 4 is 32, plus 4 more on the krypton, 36. So we're good there. Now for the last one, xenon Cl2. Okay, so maybe I should actually move these a little bit because we want them to kind of match where they're hovering over. So this is krypton. This is PCl5. is ICl5. Okay. So the last one is xenon Cl2. Okay. And that's going to be xenon in the middle again. Xenon has 8 electrons because it's on the 18th column. Chlorine still has 7. So 7 times 2 plus 8, 22 electrons we need to deal with. So we have just 2. Thankfully, it's a lot smaller. Excuse me, sorry about that. Alright, so now we have the chlorines on each side. And then fill out the octet. It's only sharing 2 of its 7. I mean 1 of its 7. So 2, 3, 4, 5, 6, 7. Xenon is right now sharing 2 of its 8. So it needs 3, 4, 5, 6, 7, 8. So that's xenon there. It also breaks the octet rule in this case. So with that all being said, this is the behemoth of Lewis style diagrams we have. So now these questions, which exhibit a bond angle that is 120 degrees, around there. So for this, first you have to actually know the electron geometry shape, okay? Alright, so for this, to find the electron geometry, we first need to figure out what the electron pair geometry number is, okay? The hybridization, okay? So, and we figure that out by seeing the amount of things it's quote unquote attached to. It's attached to one single bond, another single bond, 3 single bonds, 4 single bonds, and 1 lone pair. But in total, that's going to be hybridization of 5, okay? And if you have a hybridization of 5, that is sp3, because 1, 2, 3, 4, 5. sp3d, that is your hybridization. Okay, because S counts as 1, P 1 through 3 count as, so sp would be a hybridization of 2, which would look like that. That's an sp hybridization. Like a perfect example is carbon dioxide. That's a sp2. I mean, that's an sp. A good example of sp2 would be nh3. No, it won't. Sorry. A good example of sp2 would be like boron. Yes, boron, because each hydrogen takes 1. That is a good example of sp3. I mean, I keep skipping sp2. sp3 is like ch4. Okay, that's a good example of sp3. And then because this has a 5th one, it's sp3d. Now for iodine, we're going to treat the same. We have 1, 2, 3, 4 bonds, but 2 lone pairs instead of 1. So this one has actually a hybridization number of 6, which is sp3d2. Okay, which is, you remember, that's one of the questions they're asking, which exhibits that. Phosphorus, on the other hand, okay, is going to be, just to make sure, how did we do phosphorus? PCl5, and beryllium was just TeCl4. So phosphorus actually also is going to be, if we note it, it's going to be 1, 2, 3, 4, 5. So 5 things as well. So it's going to be 5, which is, as we discussed, sp3d hybridization. Krypton, okay, is going to be 1, 2, 3, 4, 5, 6. So krypton is actually also showing off the 6 sp3d2 hybridization, and xenon, okay, is going to be, if we count them, the things attached to it, 1, 2, 3, 4, 5. So 3 lone pairs and 2 bonds. That's still going to be 5. So that's hybridization of sp3d. So far we answered this question here, which exhibits sp3d2 hybridization. Is going to be ICl5 and Krypton Cl4. Okay. So now, with that being said, the next questions depend on the actual electron and molecular geometry. So the electron geometry for this, because it's sp3d, is going to be, if I remember correctly, trigonal bipyramidal. And for 6, it's actually going to be octahedral. So this is going to be trigonal bipyramidal. Now remember, this is the electron geometry. It gets a little bit different when it comes to the molecular geometry, because molecular geometry actually accounts for whether the bonds are actually lone pairs or actual bonds, the things attached to it specifically. So this one's also going to be octahedral. Okay, again, trigonal bipyramidal. Okay, so now let's move on to molecular geometry. What is the ratio of bonds to actually lone pairs? It's 4 to 1. And I'm going to tell you honestly, I don't have it that shape memorized, but let's just go right now, just listening out. Molecular geometry for this one is going to be 4 to 2. Okay, and this is going to be 4 to 1 as well. All right, no, actually, sorry, I miscounted. It's just going to be actually 5, because, you know, each chlorine is where the single bond is. So good news is that this one actually stays trigonal bipyramidal. Okay, because the shape name stays the same when you actually are completely full. This one here is going to be a ratio of 4 to 2. Okay, because it has 2 lone. Let me actually count again. This is not 4 to 2. I keep ignoring that chlorine. So it's actually 5 to 1. Okay, and this shape I don't know either, but I do know 4 to 2 specifically is actually going to be a square planar. Okay, that's the shape we're dealing with there. And for this one, it has 3 advanced electrons, so it's going to be 2 to 3. Okay, and that shape I do not know. Actually, I think this is actually linear, but I may be wrong. We'll have to go back and fix that. But yes, these more fancier ones I'm not too familiar with, but the point being is that this is linear because if we drew it like this, okay, with xenon in the center, the electrons kind of surround it in its x-axis, and then we have the chlorines on each end. Okay, so kind of like if I were to draw out the shape, it would be like a circle and a line that goes through that circle. So kind of end up with looking like this pretty much. If you looked at it from this angle here, okay, it'd be a straight line down, straight line there, which is why it's a linear shape. These lone pairs cancel each other out in the x-axis, and the chlorines cancel out in the y-axis. So this actually is a nonpolar molecule. Okay, just to make sure, yep, trigonal bipyramidal, it's linear. The reason why this is square planar is because you have the krypton in the center, right? And then you're going to have the chlorines kind of in the I guess the x-axis part, okay, where it literally forms like a square. I don't know, I can't draw this line properly. There, okay, and the chlorines are here, and you have the 2 lone pairs that cancel each other out from the top and the bottom. So they kind of have like a sheet that looks like that, and the lone pairs kind of stick out like that. So if you looked at it from this angle, kind of similar to the one previously, you have also a nonpolar molecule because the x-axis cancels each other out and the y-axis cancels each other out as well. I probably signed that wrong. The x-axis cancels each other out and the y cancels each other as well. But yes, this is a square planar for krypton. And one of the questions actually asking that, which has a square planar, that would be this one here, this octahedral shape. So Krypton Cl4 will be the square planar. Phosphorus is also going to be nonpolar, but it's going to be pretty much trigonal bipyramidal, to where it's like you know, phosphorus in the center, and how do we draw this again? It's going to be like that. 1, 2, 3, 4, 5. Okay, like that. And each one is going to be like the chlorine. So it's going to be quite similar to the, you know, this one here. Okay, where you have kind of like the chlorine circling about there and a line that goes through it. So if you looked at it directly, it'd be kind of like this. So they still do cancel out and everything. And each angle here, actually, as you see here, the 3 kind of splits. And I'll actually go over the angles for the other ones, but you see that these ones will actually be like 120 degrees. Okay, and then these will actually be 90-degree angles. Okay, because as you can see here, if we drew it like that, you can see the 90-degree clearly. This one, you can see the 90-degree clearly, and actually each chlorine between them is also 90 degrees. And if we went back to xenon, the electrons are what's having that kind of 120-degree angle, but we don't count the electrons. Okay, so all we have here is just really, because it's linear, it's 108 degrees. Okay, because the electrons, we don't really count them because it's not really a bond, so we don't really say that they have like a certain distance between them. So with that being said, right now only this one here, the PCl5, has that 120-degree bond that they were looking for so far. Okay, and now I'll fess up, these ones I don't know what shape they're expecting between 4-1 and 5-1. I'm pretty sure the 5-1 looks like, actually let me think of the 4-1 first. I'm pretty sure the 4-1 looks like, if I were to draw it out, if I remember correctly. Don't know what the shape is called, but it's kind of like that. These two kind of are squeezed together because the electron here is a bully. So we still have this, okay, it kind of looks like that. But the issue here is that, if I counted it correctly, the issue here is that because the electron, you know, it's kind of making sure that it's bullying them in a sense, it kind of pushes the chlorines further away from it because electrons exhibit, I guess, more of a harsher push. This bond right here would be less than 100 degrees, I mean 120 degrees, but it's still going to be around it. So we can still actually count this as a 120-degree bond. But here though, the same thing is that you would think that it's 90 degrees, right? But because that electron here is still exerting that bullying push, it's going to be something that's just less than 9 degrees. Okay, that's usually how you signify it, because when it comes to these, whenever there's like an electron involved directly in there, unlike these where the electrons cancel each other out, what happens here is that they exert their own kind of push towards everything else, literally, to where it kind of like squeezes everything. Now with this being said, this one here, okay, would look kind of like this. Okay, so we have iodine, okay, and we're gonna have the, I guess, the planar part that would be planar theoretically. Then you have the electron, and like that. I'm pretty sure that would be how you draw it. Okay, so we still have, I guess, this shape here. We kind of have the square, and then, you know, if we drew it to the side like that, but because the electron has that push up there, everything kind of squeezes in. So instead of it just being like perfect 90-degree angles, these ones here will still exhibit that 90-degree angle, because I guess they're kind of, we'll just say that everything here is kind of just less than 90 degrees. Okay, so that is the shapes I'm thinking so far, but let's actually see their name, which is why we have the Vesper sheet here and ready for us. So as you can see here, if we scroll all the way down, trigonal bipyramidal, a 4:1 ratio is a seesaw. Okay, and that is actually what we got. So we have, at least from what we drew. Okay, and 5:1 is a square pyramidal, which is, yeah, we got that too. Nice. So square pyramidal. 5, 0, okay, as you can see here, is still trigonal bipyramidal, which is what we got. and that's the shape we got. Okay, and 4, 2, if we go down here, square planar, which is also what we got. And now for the last one, 2, 3 is linear, which is also what we got. Perfect. Just was blanking out on the names for these. So now reviewing what the question was asking for, okay? Which exhibits a bond angle that is around 120 degrees? That will be the TeCl4, as you can see here between these two chlorines, okay? Based on the seesaw, you can even see here an even better example. The two chlorines at the bottom, that's kind of around 120. And also it would be PCl5, perfectly just around it. That would be what we have a whole 120 degrees between the chlorines in like the x-axis. So which exhibits sp3d2 hybridization? That would be ICl5 and Krypton Cl4, which have a square planar, specifically not square pyramidal but square planar. That would be only Krypton Cl4, because the other one is square pyramidal. As you can see the difference. Okay, and which are polar. Okay, as we discussed, so this one will be polar. Okay, so actually I'm going to highlight in green. Because of that, it's polar. This is also polar. So the first two are polar. TeCl4 and ICl5 are polar. Okay, this one is going to be non-polar because all the chlorines cancel out. This is non-polar because the electrons also cancel out. And this is non-polar because the electrons around it cancel out. Okay, so yes, that is all we have for this question, even though it was a lot. So it wasn't all we had. We had quite a bit. So let's go back to what this says. TeCl4, did we draw that correctly? Yes. Yes, for ICl5. Yep, just double checking. It's 5 and 1. Yep. PCl5, correct. KrCl4, correct as well. And XeCl2, that is also correct. So with this, we can just skip over that because we've already gone over it. But TeCl4 has a square planar. No. ICl5, it's trigonal bipyramidal, and just to make sure I was looking at it correctly, 4-1 is seesaw. That is, I guess, the shape is what it's called. So that's incorrect. So this question is already leaning towards the incorrect. But ICl5 has square pyramidal, which is correct. PCl5 has trigonal bipyramidal, correct. Square planar, so that's actually what they mean here. So this one, they don't have the correct name, but this is linear now. PCl5 has a bond angle of approximately 120, whereas it's PCl5. Yes, that is correct. And same, they did not include the tellurium as well. As you can see here, there is that bond angle of 120. It even says here, for even the seesaw, 120 in the plane and 90 above and below. So kind of like right there, this is 120. Around there, theoretically, even though it is going to be less because of the electron there. KrCl4 exhibits that sp3d2 hybridization, but not only is it KrCl4, but it's also the ICl5. And TeCl4 has square planar. That is correct. And whoops, no, that is not correct. It's the KrCl4, so that's incorrect. And TeCl4 and ICl5 are polar. That one is actually correct because of the lone pairs that don't cancel each other out there. So overall, this is incorrect. This is, I'll say, partially correct. So TeCl4 is seesaw, and what else did they miss? So let's start from the top. So TeCl4 is seesaw. Okay. Where is it? KrCl4 is square planar. Where is it? Oh, there. TeCl4 also has a bond angle of approximately 120 degrees. What else did we put? Okay, ICl5 also has a sp3d2 hybridization. Okay, I think that was everything. Yeah, I think that's everything that they covered here. And just to make sure exactly, when we're dealing with octahedral, looking at the Vesper theory, as you can see here, sp3d2, which was also ICl5 because of the because of the 5:1 ratio that it had. Because it even shows here, just to make sure I'm not seeing anything wrong, 5 bonds, 1 single pair. That is actually 6. So that's why it's sp3d2 there. Okay. So that was that. I'm gonna kind of do this for you in case you want to just